And by the way, this second paper took me a very long time to get published. So finally, after a couple of years, we got it published. So I'm going to go through some background information, and if anyone has a question, you know, if something's unclear and I need to clarify while I'm speaking, feel free to ask a question. You can feel free to interrupt or raise your hand. So what is SIF? Maybe not everyone is familiar with what solar-induced chlorophyll fluorescence is, but basically when sunlight hits a leaf, it has several different pathways. That light can be reflected, it could be transmitted, or it can be absorbed in the leaf. Now, once the light is absorbed by the leaf, it has three primary pathways. It can be re-emitted as chlorophyll fluorescence. It can be used for photosynthesis, or it can go to heat. And this is loosely termed as photochemical quenching and non-photochemical quenching. So APAR chlorophyll, which is the amount of photosynthetically active radiation absorbed by chlorophyll, it goes into these pathways. That energy is re-emitted as SIF. It goes to photochemical quenching or non-photochemical quenching. And this is what the spectrum, the fluorescence spectrum looks like. There's two peaks. There's one right around about 690 or so, 685. And then there's another peak that's actually somewhere around 740, 750. There's this other peak in the fluorescence. And you can actually extract chlorophyll from a leaf in a test tube or a beaker, as you see here. And under UV light, you can actually see the chlorophyll fluorescence. So this is an important point in that to get chlorophyll fluorescence, you don't need photosynthesis, or I should say, you don't need the dark reaction part of photosynthesis is not directly related to SIF, or SIF is not related directly to the dark reaction. There's a light reaction and a dark reaction for SIF. And SIF depends on two things, light and chlorophyll. And of course, you need light and chlorophyll for photosynthesis as well, but this carbon fixation occurs in the dark reaction. But I'm not going to go too far into this topic because I want to discuss the broader implications of chlorophyll fluorescence in the Amazon. So how do we get SIF? We basically retrieve it from the irradiance that we measure, or I should say the radiance that we measure that's being reflected from Earth's surface. So the incoming light from the sun, if you look at this right figure here, what I'm showing is this line, this black line is a perfect black body spectrum, and then this yellow is sunlight at the top of the atmosphere. Now there's gases and there's elements in the atmosphere that absorb this sunlight, and we call these absorption bands. And so this red area under the curve here, this is illustrating what we see at Earth's surface. You can see that there's a good deal of energy that's being absorbed by the atmosphere itself. And we use these dips. For instance, you see that there's a very big dip in the curve here in the oxygen band that's being absorbed by oxygen. So we can use these absorption bands to retrieve SIF. So this is an important distinction. We don't observe SIF. It's not directly observed. What we're doing is we're retrieving it from a spectra. So that's illustrated here in this lower left panel where we have the SIF spectrum transposed over the radiance spectra. And what happens is there's an infilling of this curve. And so on the right, what we're showing, this bottom right figure is showing downwelling irradiance from the sun and then upwelling radiance from the surface. And when there's fluorescence, it'll fill in this curve. So that's the basic way that we retrieve SIF from space. So I'm going to get into the papers and some background first before we get into the studies. There's been a debate for a while whether the Amazon forest greens up. Number one, whether the Amazon forest greens up at all, and whether it greens up during a drought. And so this debate really started with a science paper in 2007 by Scott Seleska. And he's very well known for doing a lot of research in the Amazon. He's associated with all the eddy covariance towers down there, for instance, and in this initial satellite observation. So this is early in the MODIS record. Remember, MODIS was launched in 2000, and we have a full annual record starting in 2001. And so this is a pretty early paper for the MODIS record. And they published this paper in Science in 2007, and it was literally, I think, a couple of hundred words. It's one page with a 2-panel figure. And it was titled Amazon Forests Green Up During 2005 Drought. And so on the surface, this looks like a very confusing observation, right? Because you would think that during a drought, you would not see vegetation green up. But that's what they saw in the data. And so this is their figure from that paper, and they're showing an anomaly. If you look on the right-hand side, they're showing an anomaly in greenness. And there's anomalously high greenness here in the Amazon. And it loosely, the pattern, as you can see, it loosely matches this, this negative anomaly in precipitation. And then there were a series of papers that came out to kind of refute this finding. For instance, this one was titled, Amazon Forest Did Not Green Up During the 2005 Drought. And so this is where the debate really kind of takes off. And what they show in this paper essentially is that if you do no screening for clouds and aerosols, that you will see this high anomaly, this positive anomaly in greenness. But once you do the screening and screen these things out, you don't see it. So some background before we dive more into the debate. I want to give some background on why, some of the foundations on why people are arguing that Scott, even though the data shows an anomaly, that it might not actually exist. It's an artifact of the data. And this argument is rooted in reflectance and the BDRF of reflectance. So basically, BRDF is the bidirectional reflectance distribution function, and this is a mouthful. But basically, this is how we model the reflectance of light off of a surface. And so there's many different models. If you just go to Google or Wikipedia or something, you can find tens of these models. And essentially, it can be modeled in many different ways. But the three that I have here are general illustrations of how light might be reflected off of the surface. This first one is a diffuse or Lambertian reflectance, in that you're getting the observer from any direction will see the same amount of illumination coming off of the surface. And then glossy, you can think of a glossy surface that the reflectance is somewhat diffused in a certain direction. And then a mirror is reflecting all of the illumination into an opposing direction. And so that's what we have here. And so in reality, Earth's surface is very heterogeneous, and so you have a lot of different reflectance distribution functions, essentially, that can come off of the Earth. You know, some parts of Earth are very Lambertian. Some are glossy or mirror-like, especially the ocean has a very strong glint to it. So this is the BDRF, and the surface reflectance products, for instance, MODIS 9, MCD 43, these reflectance products are BRDF corrected or not. MODIS 9, it does not have a BRDF correction, although from what I understand, they did develop a BDRF correction, but never applied it to the MODIS 9 data. But the MCD 43 and the MIAC data does have a BRDF correction. So a little more on this BDRF effect. So what does BDRF mean for satellite observations? And we term this sun sensor geometry. So what really matters here is this geometry between the sun and the satellite. And this figure is illustrating a number of different things. It's illustrating the solar zenith angle, which is this theta sun, and then the viewing zenith angle, the theta satellite. And we also have azimuth angles. So we have solar azimuth angle down here. I should mention this point in the center. This is the point that is being observed, and the point directly above that. So this point could be any point on Earth's surface. Okay, and then these are the geometries that are associated with that point. So like I say, we have solar azimuth angle, viewing azimuth angle, and then I marked PA here. This is phase angle. This would be the angle between the sun and the satellite. And when this angle is 0, that means that the satellite and the sun are in perfect alignment. And the sun can create a hot spot on Earth's surface. And in this case, at 0 degrees, the satellite would be observing directly that hot spot. And so our observations from the satellite of reflectance can be impacted by sun sensor geometry, the alignment of the sun and the sensor. But most satellites are not observing just a single point. They're taking a swath over Earth as they pass over Earth's surface, and that's what I'm illustrating here. This is the Sentinel-5 precursor, Sentinel-5P satellite. The sensor is Tropomi. So throughout the rest of the talk, you'll hear me mention Tropomi data, and that's what I'm talking about is the Sentinel-5P. And it has a very wide width. You'll see here that it's about 2,600 kilometers wide. So what we have is the satellite is actually sampling many different points on Earth's surface at the same time. It's not sampling just one point. And each one of these points on Earth's surface, you can think of it as a grid here in this lower figure. Each one of these footprints is going to have a different size, and it's going to have a different sun sensor geometry. So as you scan Earth's surface, you're going to have a variety of different effects from a sun sensor geometry. You're going to have what we call these BRDF effects. So when you're looking at reflectance data and SIF data, to some degree, your observations or SIF retrievals are going to be affected by this sun sensor geometry. And on the right, this globe, this is just an illustration of one swath. Actually, this is illustrating 2 different swaths of Tropomi on Earth's surface. And this is another illustration of a swath on Earth's surface by Tropomi. The one that I'm most interested in for this talk is this lower left one where it shows phase angle. So if you remember, phase angle are the geometries between the sun and the sensor. And you can see a hot spot here where the phase angle is 0 or near 0. And so in this case, when Tropomi is in this spot, these soundings here are going to be virtually aligned with the solar zenith angle. So it'll be observing this hot spot. And you can actually see this in the data itself if you just plot the data and take a look at it. So what I have here on the left is a gridded version of the Tropomi data for an overpass. And I can't remember the spatial resolution of this data, but what matters is if you look at this swath, you can see a swath here, and you see a hot spot. You can see these red grid cells. These are grid cells that have very high SIF values. And as you go towards the edges of the swath, it tends to be the same color. They tend to look very similar. But you can see this hot spot effect right here in the middle of the swath. And on the right-hand side, this is ungridded data. So this is just a representation of the soundings themselves. This is vector data. And where this blue meets the orange would be 0-degree phase angle. And so you can imagine that these hot spots that we're seeing here align very closely to where phase angle is near 0. So this BRDF effect is very important for the SIF data. You need to take into account sun sensor geometry when you're doing analysis, because obviously, I should mention this is over the Amazon. And so much of this area is going to be very homogeneous in land cover. It's all going to be forest, much of it. And so really the difference between these grid cells, is it because these grid cells have truly higher SIF, or is this an artifact of sun sensor geometry? So the sun, throughout the year, the sun itself, I should say, the position of the Earth relative to the sun can impart a seasonal artifact in reflectance in SIF data. And what I'm showing here is, if you look at the top, this is during the equinox in March, which also occurs in September, obviously. In the sun, this is when the sun is aligned directly over the equator. But in the solstices, you get the sun pointing at either the Tropic of Cancer or the Tropic of Capricorn. So you have this kind of modulation of that hot spot from the sun on Earth's surface throughout the year. And so not only is viewing geometry important, but the position, I should say, the position of Earth relative. So back to the debate. So a lot of this, the papers that refute Scott Seleska's result say, well, you're using uncorrected data. It's not BRDF corrected. If you take into account the BRDF effect, then we're not seeing this anomaly in greenness. And so that's what they're showing here. I believe this paper was by Doug Morton in 2014. And what they're showing here are these gray lines. This is uncorrected surface reflectance data. And then the black line is corrected surface reflectance data. And they show the histograms. So you can see that this histogram shifts greatly towards 0. And so they argue here in this paper that that the effect that they're seeing is an artifact of sun sensor geometry and not an actual increase in greenness in the Amazon. But Scott Seleska responded with a paper and said, yeah, that might be true. The BRDF correction may reduce the magnitude of the greenness that we see, but we're still seeing a green up, and it's statistically significant. And so what Scott did basically in this paper is just test Douglas Morton's results for a statistical significance. And it's still statistically significantly greater than 0. So they argue that, yeah, we are indeed seeing this green up during the dry season and during this drought. Or I should say they saw a positive anomaly in greenness during the drought. So what does the in situ data tell us, though? So they began a network of flux towers in the Amazon in 2000. We have data at starting in 2000, and a relatively fragmented record among the different towers that are there. But this is what they show. So each column here is a different eddy covariance tower. At the bottom, I've labeled whether they're in forest or pasture. And really, what I'm interested in, what I want people to focus on is this first row at the top. This is a gross ecosystem productivity, or GPP. And what we see is an increase here during the dry season. This shaded area in these graphs are the dry seasons, okay? And notice that the dry season in the Amazon comes at the last half of the year. The wet season occurs in the first half of the year, loosely speaking. And what we see at these eddy towers is for these forests, all three of these forest sites, we see an increase in photosynthesis during the dry season. And this is the same period of time that Scott was seeing a green up. And we also more recently have phenocam data that actually shows us this. And there's actually a paper, I didn't put it here in my presentation today, which is unfortunate, but there is a paper that was published just last year that actually has a time-lapse video. And you can actually watch the canopy here in the Amazon forest green up during the dry season. It's pretty phenomenal. But what they're showing here are just a couple images in line plots that is showing this green up phenomenon during the dry season. I just want to point out in these figures on the right that they're starting the x-axis on July. So this is July to December, and it's shaded because this is the dry season. And what they're showing here is if you look at this panel B, they're showing an increase in EVI from the camera and from MODIS MIAC EVI. And remember, this MODIS MIAC EVI is BRDF corrected. So they're seeing this green up at the site and in the MODIS data. I also want to point out here in this third figure, they're seeing during the same time, I should say, you can see PARs increasing during the beginning of the dry season. But after September, it's decreasing PAR, and the reason why is because the solstice is starting to occur. This is after the equinox, and so you're getting a decrease in PAR, and clouds obviously could be playing a role in this. But basically, you're getting increased phase angle, which means that the sun sensor geometry itself would serve to reduce the greenness, or if they were to observe SIF here, it would serve to decrease SIF rather than increase it. So they're seeing increased greenness, even though they're seeing a decrease in PAR. And this is important because we'll go back to that when we look at my results. But what do the models predict, and what do they suggest we might see? So Natalia Restrepo-Coupe, I showed her figures from the eddy towers. I should have mentioned her earlier. After they published their paper on the eddy towers, they came back and they looked at the models, several Earth system models, to see what they had to say. And if you look at these sites again, the shaded area is the dry season. And in each case, you see this black line, you're seeing, the black line is the eddy covariance tower. You're seeing an increase in GPP at all three of these sites during the dry season, but the models aren't capturing that. They're relatively flat or declining during this time period, but none of these models obviously capture this increase in GPP. So it tells us, well, maybe we have an issue with our models too. And you can imagine that the Amazon, right, is massive. And so we have a lot of photosynthesis there. And so this is very important for the global carbon sink. So not modeling the Amazon and the tropics as a whole correctly could be a real problem. So, we looked to address this debate by looking at the chlorophyll fluorescence data from Tripomi. And obviously the Amazon, it's a very cloudy region. So previous platforms like GOSAT and OCO2, it's very difficult to investigate this area because their spatial resolution is, well, GOSAT has a very coarse resolution, and OCO2 soundings have a very, actually a very fine resolution, but the swath is tiny. And so it's very difficult to elucidate these results from those platforms. But Tripomi has a very wide width, and it has a global near daily revisit time. So we chose Tripomi to see what we could dig out of the data to see if we could also see this dry season increase in fluorescence. And here we're just addressing the dry season itself. We're not looking at drought because when I started this paper at this time, we only had 1 year of Tripomi data. And we also looked at greenness. So we looked at MODIS and also photosynthesis from the vegetation photosynthesis model, VPM, which is a light use efficiency GPP model that we produce in Dr. Xiao's lab. So this is what we see. So if you just look at the top panel, the top row, A, B, and C, I'm just showing SIF here. So we gridded SIF. We took a 16-day mean for SIF. Tripomi has a 16-day repeat cycle. And so we took a mean for those 16 days. And the idea behind this is this negates a lot of the viewing geometry effects, not necessarily solar zenith angle, but the viewing zenith angle. The idea is that if you have a sample from all 16 days, then you're sampling over the entire distribution of the viewing zenith angles. Now, of course, the Amazon's very cloudy, so you're not going to have samples every day for the whole Amazon. But this is why we did a 16-day mean. And we divided the dry season up into three parts. We divided it into the early dry season, mid dry season, and late dry season. And I should say that these are loose definitions because the dry season is different across the Amazon. The Amazon has a precipitation gradient. So this is not a hard and fast rule for the entire Amazon, but we needed to come up with some sort of threshold for the basin scale. And so if you look at the early dry season and mid dry season, there may not be a noticeable difference here to you immediately. But if you look at the late dry season here at the top right, you see a lot of dark blue color. That means higher SIF. So SIF greatly increases. You can just tell by looking at this figure. And then D and E, we actually took the differences between these figures A, B, and C. So this is the change in SIF between the early to mid dry season, and then the change in SIF from the middle to late dry season. And you'll notice immediately that there was a big decrease in SIF here in this south central and south part of the Amazon basin. And if you look over on the far right at the percentage of forest cover, these are areas that have very little forest. So this is mainly cropland. And the reason why we're seeing, why we suspect we see such a strong decrease in SIF here is simply because they're harvest. This is a harvest period and their replanting period. And it probably also has to do with phenology of the vegetation that is not harvested or replanted. But if you look at the mid to late dry season, you see across the entire basin, nearly the entire basin has a very large increase, relatively large increase in SIF across a pretty wide scale increase in SIF. So that's the basin scale looking at it. And that's just gridded. We gridded the data so that we could look at it there. Now, for the rest of the analysis, we used ungridded data. We didn't grid it at all. And we broke the data into two different parts. We looked at SIF in moist forest, and then SIF in seasonally moist forest. And what we mean by that is moist forest is forest that has more than 2,000 millimeters of precipitation a year. And SIF that's seasonally moist has less than 2,000 millimeters of mean annual precipitation. So if we look at this top figure, we're seeing that during the late dry season, especially, we're seeing a large increase in SIF for both moist and seasonally moist forest. We're also seeing, and what I did is I put GPP from the K83 eddy covariance tower here. Now, K83, the data we have for this was from 2000 to 2005. So here I'm just showing a mean of GPP for those 5 years. We don't have AO covariance data for the actual time that we have the Tropomi data, but it's still evidence that the tower is capturing an increase in GPP, and the satellite is capturing an increase in SIF for both of these forest types. If we look at panel B, now what we're showing, these two SIF lines are the exact same SIF lines from panel A, but we're also, this time, instead of showing eddy covariance tower GPP in green, we're showing EVI for both moist forest and seasonally moist forest. And so we're showing that that we're also seeing increased greenness, and that this increase in greenness and SIF match very well. Let me pop these two questions in here. So this kind of begs the question. So is phase angle driving the increase that we see in SIF and greenness, or is cloud cover possibly driving the increase that we see in SIF? So what I did is I put this line here, and this line indicates the point in time in which phase angles are increasing for all of the Amazon. And so we're seeing an increase in phase angle, which would serve actually to decrease assuming everything constant, this increase in phase angle would decrease SIF and decrease greenness, but we see that they keep rising after this point. And as far as cloud cover, we have satellite reanalysis data for PAR at the top of the atmosphere and PAR at the top of the canopy. And so what I did is I took the difference of these two to estimate the amount of PAR that's being absorbed in the atmosphere or is being reflected by the atmosphere back into space. And so this is a proxy for cloud cover. And so if you look at these two orange lines down at the bottom, well, what I've done here actually is I've plotted PAR at the top of the atmosphere, the top of the canopy, and then the difference between these two using the satellite reanalysis data and data from the K83 tower. And they agree very well, as you can see. But the point here is that in the late dry season, we're seeing a decrease in PAR at the top of the canopy. And we're seeing an increase in PAR that's being absorbed or reflected in Earth's atmosphere. So this indicates that PAR, I should say, the phase angle and the cloud cover is not driving this increase in SIF. Actually, these increases are overcoming whatever diminishing effect these changes in PAR may have. Hopefully I explained that right. It's a little difficult to understand. So, but this begs the question, all right, well, still SIF, isn't this affected? Doesn't this have BRDF effects, just like the reflectance data? You know, Russell, you're using SIF data that is not BRDF corrected. Why aren't you doing that? So remember, I mentioned phase angle. The closer the phase angle is to zero, it creates that hot spot that I showed you in the SIF data. And so what I did here is I just took, I had millions of soundings in the Amazon for this study period. So what I did is I just took a random sample of a million random points in the data to show this. And you can build up this curve, and Philip Kohler in his paper found the same exact thing, and he has this same nearly same figure. The equation at the top is the same as what he found. And so you can see that the closer you get to zero, the stronger effect that the sun sensor geometry has on the SIF signals. So, but you get to these higher phase angles, especially between 40 degrees and 60 degrees. There's very little effect in I should say that the phase angle has very little effect on the SIF signal. It's nearly flat through here. And so what we did is I think this is in the actual paper. There's other figures in the supplementary. So what we did is we broke this down by phase angle to illustrate that no matter what window of phase angle you look at, you're seeing this increase. Even in here where phase angle, for instance, between 40 and 45 or 45, 50, 55, 50 and 55, et cetera, you're still seeing these increases in SIF at these phase angles where we would expect the effect of sun sensor geometry to be extremely minute. And you can also take this function here that we have and apply it to all of these curves here, and you'll find that the change in SIF is much greater than what could be explained by sun sensor geometry alone. And we could talk about it more if people want, but there's been some hesitancy to prescribe some sort of BRDF correction to the SIF data. But here what I'm showing is that perhaps it's not necessary in these instances to even correct the data, because the change in SIF, even though it's small, it's much larger than what could ever be attributed to sun sensor geometry. Besides, it agrees with BRDF corrected surface reflectance data. It agrees with the phenocam data. It agrees with eddy covariance tower GPP. So all the evidence is really stacked against this argument that the green up that we're seeing in space in the Amazon is completely a data artifact. Actually, there's been no evidence to support that, whether it's in situ or that, at least that I've seen. There's no in situ or even spaceborne evidence to suggest that this is not happening. We know from leaf litterfall data, the phenocam data I showed you, that there's definitely a leaf flush going on and leaf emergence going on during the dry season in the Amazon, especially for these moist forests. So let me check the time. I know that the time, so I'm almost done. This next paper, I only have a couple of figures. So the next step that we wanted to take was to take a look at the anomalies in SIF during the last two El Niños and La Niñas, and we did this with GOM2 data. And one reason we wanted to take a look at this is this is from Junjia's paper in 2017. This was a science paper, a very important paper. And as everyone knows, we had a very strong, perhaps the strongest El Nino on record during 2015-16. And this caused a dramatic change in the rate of CO2 in the atmosphere. And Junjia looked at this and attributed these to some different drivers in tropical South America, Africa, and then Southeast Asia. And part of this dramatic increase in the rate of atmospheric CO2 was attributed to a large decrease in GPP in the Amazon during the El Nino. And so we went a step further and we wanted to look at the dry season, because we know that the GPP increases, fluorescence and greenness increase during the dry season. So we were curious whether this decrease in photosynthesis could be attributed to the dry season or not. And just a word on what El Nino is, what INSOs are. I read all the papers I possibly could on this, especially for the Amazon. And what I found is that in many papers, they don't tell you what they're defining as El Nino or La Nina. Some papers use a calendar year. Some people use what I call an INSO year. the INSO phases do not occur during a calendar year. The INSOs flip during the middle of the calendar year around June or July. And so that's what I'm showing here. These red bars, these are El Ninos, the blue bars are La Ninas. And you can see here these tick marks on the x-axis is January. So you can see in the middle of the year, you're getting a flip-flop between El Nino and La Nina. And so we chose these periods to look at. So remember, we're looking at only the dry season. And so we took a look at these two La Ninas here and these two El Ninos here. And the other years we just took as normal and calculated their means. And so that's how we calculated the anomalies for these 4 INSO events. So I'm just in the paper, there's results for September. We looked at September, the month of September specifically, and they're very similar to these results here. So I'm just gonna show the results for the entire dry season. The top row, the top row is gonna be the La Nina, and the bottom row is gonna be El Nino. And so these are the anomalies, departures from normal. The first column is GOM2, and then we have VPM, GPP, and then MIAC, EVI, and MIAC, NDVI. Remember, these are BRDF corrected. And although the top row, this La Nina, is actually indicating maybe, and I should mention these histograms below here reflect the data that's above here. These differences in SIF that you see here, you could see here I have 2007 dry season, the blue. So the blue would be La Nina, and the red histograms are going to be El Nino. And you can see here from this top row, you see a lot of red. So it's indicating that there was some decreased SIF, I should say abnormally or anomalously low SIF in many parts of the basin. You look at the El Nino, and there was anomalously high SIF in large portions of the basin. And the spatial patterns somewhat agree with each other. So what this indicates is at least for the dry season, there's no clear signal that there was a big decrease in SIF, greenness, or GPP. If anything, they're at the basin scale. Remember, this is basin scale. Maybe the El Nino actually enhanced productivity a little bit during the dry season. And this bottom row, what I've done, this bottom row is the same as the histograms above, but I filtered it only for moist forest. So I'm showing histograms for the Amazon basin and the moist forest, and they were very similar to each other. However, I want to point out, although these anomalies are statistically significant, these histograms, if you look at these histograms, these are statistically significant. They're statistically different than 0, but they're very, very small. So you see a lot of color on these figures, but if you look at the legends, these are very, very, very small anomalies, extremely small. So it also tells us that the change in greenness SIF and modeled GPP from year to year is extremely small. And then we looked at the 2010 11 La Nina and 2015-16 El Nino, and the results are very similar, although the differences were not as large as the previous two. And you'll see some different spatial patterns that are popping out here. For instance, you'll see the Amazon River itself. It doesn't tend to agree with the rest of the basin. For instance, you see a lot of red here, and there's some blue in other parts. If we go to the previous slide, you'll see that in the top row, you actually see a lot of blue positive anomalies here along the river corridor itself, and then red elsewhere. So there seems to be a different effect for these areas that are inundated. So that's an important point. But we just wanted to take a a whole basin scale look at things, and our real focus in this paper was moist forest. But there's a lot of other information that could be dug out of these results. So with that, I'd like to say thanks to my funding sources, which have included obviously Caltech and OU, NASA, USDA, National Science Foundation, Oklahoma EPSCoR, and GeoCarb, which, by the way, GeoCarb will be launching in a couple of years. It's a new NASA satellite that'll be geostationary and will provide us daily scans of North and South and Central America, SIF and trace gas retrievals. And here's my contact information and in my WeChat QR code if you want to contact me later if you're interested in collaborating or need some data. With that, I'll take any questions.
Okay, thanks, Russell, for the comprehensive study of the Amazon rainforest and by soil fluorescence. So yeah, we can have a couple of minutes for the questions. First, yeah, I think we can do the two platforms at the same time. If someone in Zoom would have any questions, you can unmute yourself and ask Dr. Russell directly.
Oh, I have two questions. It's a nice presentation. Could you hear me clearly?
Yes, I can hear you.
Okay. The first question is about the late dry season you defined in the paper. You told us that October and November you define here is the late dry season, and that's the pre-monsoon season in Amazon region. And here you see GPP, NDVI, or EVI, I can't remember it clearly. Is it possible for the CF increase due to more rainfall because this is the pre-monsoon season? The precipitation increase significantly, and also the energy is not limited here. I mean that is it possible for this region here is the trade-off between rainfall and solar radiation? So that's caused the CF and other vegetation index increase here.
That's a good question. So I don't have precipitation plotted in any of these, but what I would say is that I'm trying to look for a figure. Let me resize this figure real quick. There's actually here. Let me do this. So the timing of precipitation across the basin is very different. So the signal that I'm showing is kind of a basin-wide or for all moist forests clumped together, but really the start and the length of the wet season and the dry season is different for all of these, for depending on where you are in the basin. So sorry, I'm just going to try to show the rest of this figure. So in the paper, there's actually these panels here that are showing precipitation. I'm showing 12-month total, and then also the first month with more than 100 millimeters of precipitation. And so you can see here, I haven't considered this too closely, but you're right. So I think that just the vegetation obviously is going to want to take advantage of the sunshine. It's going to want to avoid herbivory by insects and also take advantage of rainfall. What I did notice is that I think really, and I think more research should be done on this, is I think that the productivity in any dry season has a lot to do with how wet the preceding wet season was. So I actually put a figure here towards I put some extra figures in here so I can make some of these points. So let me enlarge this again so we can talk about it, and then I'll point a couple things out. So here, what I did is I have the INSO graph again in the background. The blue lines are precipitation anomalies. This is actually figure 1 from my RSE paper. And then I have PAR at the top of the canopy in red. But what I want to point out is remember in these two La Niñas, we actually had negative anomalies in SIF, greenness, and GPP, which doesn't seem to really fit the idea. And I think one reason why is if you look, this La Nina here was preceded by low precipitation. So if you look at this peak here at the very beginning of the record, this is pretty low relative to the other peaks, the blue line, if you look at these blue lines. And also, if you look at this other La Nina that we looked at, this 2010, remember we're looking at the dry season. So we looked at 2010 dry season here. Well, what came before that? There was actually a weak El Nino, and precipitation was anomalously low. So both of these La Ninas were preceded by, I would say, like a drier wet season. And so I discussed this in the paper, is that it's likely that the productivity that we see is largely dependent on this rainfall. So if you look at this El Nino here in 2015 and 16, it's very strong, right? Mm-hmm. But it's preceded by a relatively normal wet season. So perhaps there was enough rainfall in the wet season to help delay vegetation stress, if that makes sense. Whereas in these years, so perhaps vegetation productivity during the dry season is not related to INSO. It could be more directly related to how wet the wet season is. And of course, I'm using INSO here, but you know, these droughts are also driven by other oscillations like the North Atlantic oscillation. So there's other things going on other than INSO. But often we look at INSO events as driving a lot of the climatology we see on Earth. But for the Amazon, there are other things contributing to these droughts and these anomalies. So does that help answer your question?
Yeah, thank you. Because we typically attribute the rainfall anomaly to the tropical North Atlantic sea surface temperature and INSO events. You mentioned here the La Nina events also maybe make contribution to the dry season or drought events. It's interesting. And also I have another question about the how to verify the SIF data in this region. You know that the cloud here is too thick, especially in the north part of the Amazon basin. And also the observation station here is too few. So how to verify it here? And also some recent paper indicated that SIF, GPP, LI, or NDVI have the different signals in the dry season or the drought events. Which one do you think is more reliable? And also, you mentioned in your presentation, you mentioned the hotspots in the Amazon basin with very high SIF data value. It seems it shows as a line. And how to confirm it is a real signal and not the noise? Sorry, the question is a little bit long.
Yeah, no,
it's better to shorten your question. Yeah.
No, these are great questions. So, the validation of the SIF, basically, this is a harder thing to do, right? So, for instance, if we use surface reflectances in a light use efficiency model, we estimate GPP. We can compare those estimates to an eddy tower, right? So like FluxCom GPP, VPM, MODIS GPP, all these GPP data sets that have ever been produced, we compare them to the flux towers. You know, unfortunately, we don't have a comparable for that for SIF. But we can, obviously compare them to other satellite data. So that there are some differences, important differences in the SIF data that need to be kept in mind. And I also have a couple slides on this. So one of them is that SIF is not as affected by clouds as reflected energy. And SIF is emitted energy. You can think of like a light bulb emitting energy. And the clouds over a city at night is diffusing a lot of that light. It's not completely blocking the light. And in Louis Guanter's paper, he shows differences in SIF and NDVI and cloud optical thickness. And looking at these figures, you can see that SIF is not as affected by cloud cover as reflectance data. However, SIF is very, very noisy. It's a very noisy signal. And so what we do to reduce, and you can go back if you're interested and look at the PNAS paper. In the supplementary, I provide a bunch of tables that estimate uncertainty. And the reason why I'm able to get the uncertainties so low is we're averaging over large space, over large amounts of time. So a single sounding will have a high error. But if you take 30, 50, 1,000 soundings and average them together, your error becomes much lower. And so there's a trade-off there, I would say. In the reflectance data, we have high confidence in the soundings. For SIF, that's not true. The confidence that we have in SIF, like I say, is in the measured uncertainties that we can show. But also its agreement with changes in greenness, because remember, SIF is a product of PAR and chlorophyll in these vegetation indices. No, NDVI is going to saturate in the Amazon, so NDVI is virtually useless in the Amazon. So what I'm thinking of is NIRV or EVI. They match SIF very well at coarse spatial and temporal resolutions, and it's because both of these signals are being driven by canopy chlorophyll content. So the second part of your question, I think, was it's related to the same thing. So I showed you the hot spot in the SIF data, and you can see in the middle of that overpass there's a hot spot. So the idea, and this is a figure that's in a paper that's under review, is what I'm showing here is the viewing zenith angle for Triphomi soundings for a single point on Earth. And this is actually for the desert in China, a desert, Taklamakan. I know I didn't say that right. You have a Chinese name for it. But I'm showing a sounding over 16 days for a single point in the desert. And the point I'm making here is that you can take, if you have soundings each and every day, you can take a mean of the SIF over these soundings. So what you're doing is you're averaging out the SIF signal over all the viewing geometries. And you're really averaging out the effect of the viewing geometry. In fact, what we can also do is you can take an 8-day mean, and you can imagine looking at this figure, the viewing zenith angles the first 8 days and the second 8 days are the same. And so you can actually take a mean of the first 8 days and the second 8 days, and with some degree of confidence and make a comparison for that point on Earth over time. So this is the idea about averaging. So that overpass I showed you was a single overpass, one moment in time. So this is, if you go back to Philip's original paper on the Triphomi SIF data, he says in the abstract, you need to take sun sensor geometry into account if you're going to do analysis. And this is exactly why. you need to find a way to remedy this. And so I spent a lot of time before I wrote my PNAS paper struggling with this to figure out a way. And the best way I could figure out was to take 16-day means. So that's why you'll see in the PNAS paper, I take 16-day means on all of my x-axis. My time axis is always 16-day intervals, because I'm taking an average over that 16 days to get a somewhat equal sampling over the distribution of viewing zenith angles. But this doesn't solve the solar zenith angle problem, but it at least marginalizes some of the sun sensor geometry effects.
Thank you. It's interesting.
Mm-hmm.
Okay, and Russell, there's a question in the chat box. And Xiangzhong is curious about the relative importance of photosynthetic capacity, flash of new leaves, and LAI in the increased GPP during dry seasons.
Okay.
Yeah.
Let me see. Is there a way I can look at
the chat box?
The chat.
Not WeChat, just in the chat box of Zoom.
Yeah, I'm trying to open it up. Hold on.
Okay.
Perhaps I can just ask here.
Yeah, you can ask directly.
Hey, Russell, thank you for the very interesting talk. And so I'm also following work. I'm just curious about this green up or the increase of GPP. And I think for the increase of EVI, and they more reflect the amount of leaves that increase during the dry season. But for GPP, it could also due to the increase the photosynthetic capacity of some leaves. Maybe some new leaves flush out, so they're younger, they are stronger at photosynthesis. So I just want to hear about your thoughts on the relative importance of this two.
Yeah, you hit the nail on the head. So that's exactly right. So what's going on is these older leaves, they have less photosynthetic capacity, and they're going through senescence and falling off. And then you have younger leaves that are coming out, and they have higher photosynthetic capacity and a higher chlorophyll content. So that's definitely what we're seeing. So two things is the leaf area is going to be increasing, right, during leaf out, and the photosynthetic capacity is also. So both of these are playing an important role that we're seeing in the changes in greenness and SIF. So that's why that's why, although the phase angle of the sun, the illumination geometry, the phase angles are increasing, and you're getting less PAR, but you're getting more SIF and more greenness. The only way that can happen is if you have higher chlorophyll concentrations, more leaf area. There's more chlorophyll in the canopy, and that's exactly what's going on. That's and we see this in the litter fall data. We have they have leaf litter fall traps in the Amazon, and they have for 20 years. So we've known about this seasonality in leaf flush for quite a while. Yeah.
Oh, okay. Thank you for the answer. So, but based on your experience, which one do you think is like more important, quantitatively? Have you guys looked into that?
More important? Do you mean what's more important, LAI and photosynthetic capacity?
Yeah, more leaves or more younger leaves?
My general feeling is that the number of leaves won't be changing dramatically, but what is happening is, especially in the top of the canopy, that we're seeing these sun leaves. You know, there is a big change in chlorophyll content. You know, if I can send you that paper if you want, where they have the time lapse video of the canopy. And some of these trees lose all of their leaves. They completely shed all of their leaves and then flush out again within just a matter of a month or so. So over the period of a year, you know, the leaf area is not going to be very different. But the chlorophyll content is the main driver, I think, that we see in a lot of the seasonality.
Okay, thank you.
If you have more questions, you can unmute yourself. Okay. Actually, I have one question about the phase angle.
Sure.
Seems you normalize the BRDF by the phase angle, but sometimes I think phase angle is not very accurate. For example, if the phase angle is 0, you always look at the whole spot, right? But at different view zenith angle, you will see different proportion of leaves in view.
Right.
For example, at nadir view, you will see more soils. If you look at the Earth at a large view zenith angle, then you can see more leaves in view. So although the phase angle is 0, they can still be different.
Yeah, you're exactly right. Yeah, you're entirely right. So that's one reason why there's no like purely geometrical basis for correcting the SIF. So I should say, remember the BRDF, it's bidirectional reflectance distribution function. SIF is emitted energy, it's not reflected. And the canopies are, there are many different vegetation types, from grasslands to forests, and then there's mixed pixels, right? So you may have a sounding that has 10% forest and 90% grassland. The clumping of the canopies, these canopy characteristics have a very strong influence on the signal and the escape of SIF from the canopy. That's why there's been a large, I should say, people have suggested various ways to correct the satellite-based SIF data. But so far as I'm concerned, I haven't seen anything that has convinced me that it's robust enough that we should apply some sort of correction to all the SIF data. Can we really assume that all surfaces act the same way? Can we really assume that that the relationship between, for instance, some people have suggested correcting SIF using reflectance, and they think that the escape of SIF from the canopy is very similar to the reflectance. So why can't we just use the same functions? And I haven't seen robust enough evidence to suggest that we should. And using scope model, and we have a new model called CLIMA, and I've run some simulations, and we're finding that the canopy structure really matters. And this relationship between the fraction of SIF that escapes the canopy and reflectance, this relationship is not static across all canopy types. So I think that the more important thing is finding ways, like I did in my PNAS paper, to show that these changes are occurring through time without correction. Because even if you correct the data, right, how do you quantify the uncertainty that's imparted in your data from the correction itself? So you kind of get into this problem to where you can now make the argument, oh, well, the differences are because of your correction, your BRDF correction, or this algorithm wasn't correct. So I think that the most powerful way to do it is to average the SIF soundings over space and time, to reduce the noise and to reduce the viewing geometry effect. And once you do that, and if you can show the changes are bigger than what you would expect due to solar geometry, illumination geometry, I think to me, that's a more powerful argument than correcting the data and showing it, because then you'll have people come back and say, oh, well, does it look that way if you don't correct the data? Or what if you correct it this other way? So that's just my general feeling on it.
Yes, it's difficult to have a robust method that can be approved by all the people.
Yeah, and like you say, the fraction of shaded leaves and sunlit leaves are going to have an important contribution to your signal.
Yeah, so that's why I use the phase angle for the
Right.
normalization. Yeah.
In the soil, like you say, SIF can actually be reflected by soil. People don't realize that. And SIF can be reflected by the woody biomass as well.
Yeah, that's true. That's true. Okay. Any more questions? Okay. Just now I saw that the variation of SIF at the seasonal cycle is larger than EVI, right? So as EVI is a reflectance, SIF is radiance based. So have you ever tried EVI times par to normalize the unit?
No, I have not. I have not tried that. That might be interesting to do that.
Yeah, because I'm not quite sure whether I'm curious about the extra value or the additional value of SIF compared to EVI, and because EVI contains much of the canopy structure information.
Right. Yeah. So in the Amazon, at least, these, even though we know that EV or NDVI saturates in the Amazon, right? But in truth, there is a saturating effect to EVI and even NIRV. That's not linear. And so there is a non-linear effect there, but SIF is an additive signal. So as far as we know, that there's not going to be a saturation of the SIF. So in these very intensely green areas, this magnitude of change, if you compare the magnitude of change in EVI and SIF, may not be they may not be directly comparable, and they may not provide too much information. That is interesting, though, to think about, because for instance, if you use these vegetation indices and light use efficiency models, the saturation effect might be important in places like the tropics. And where you don't have this saturation effect in SIF. So relatively speaking, maybe there could be in this respect, maybe there could be an underestimation in the magnitude of productivity.
Because from your figure, seems EVI and PAR have the same trend. So if we use EVI times PAR, then EVI times PAR will be closer to SIF compared to SIF, right? Then what's the additional value of SIF? Well, SIF contains the information of the origin or the photosynthetic capacity. If that's true, that will be cool. I think Troy in your group, he has a paper in PNS, and the fluorescence yield contains some information of photosynthetic capacity in the cold regions, and seems not in the
I think that this could so SIF divided by incoming PAR would be SIF yield, and we can kind of guesstimate what SIF yield might be at the site, but for the satellite, that's going to be very tough, because we don't know the incoming radiation for these. We know the reflectance, the irradiance, but we don't know, or I should say radiance. We don't know the incoming amount of PAR. The data I'm showing here, we did include, I think, up to a cloud fraction of 0.8 or something. So for when these soundings are made, that point in time, we have to remember that these soundings are taken at a certain point in time. We don't know PAR at the top of the canopy when these soundings are taken. So the best you can do is to use like ERA5 reanalysis data, which has hourly data, but still it would be a pretty rough approximation of what the PAR might be in the top of the canopy. And so I think getting like a satellite-based SIF yield may be impossible. I don't know if anyone has tried it or not. That'd be very useful in us understanding photosynthetic yields as well. As if we could get to some of this information, we could maybe solve for photosynthetic yield using SIF yield. But if we have reasonable estimations of non-photochemical yield quenching. Yeah.
Okay. 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 So we can still have 1 minute question. If not, we will stop here.
Well, y'all are taking it easy on me. I saw Jingming was here.
Oh,
I was scared of him. I see Yao is still here. I'm kind of afraid he may also ask a question, but if not, I guess I did okay. Yao Zhang is an old.
Yeah, Yao Zhang is there.
Yeah. Old friend.
Hi, Russell. Sorry, I missed your first part of the talk.
Oh, it's great. Good to see you.
Good to see you. Very impressive studies.
I have to thank Yao. It's his fault that I got into the SIF. So he's had a large part and large role in this work. So I should acknowledge him and thank him for his help.
Yeah, Yao did a very great job on SIF, even several years ago, I think. Okay, so as we don't have more questions, so thank you very much, Russell. Yeah.
Yeah, and I saw someone just ask for the link to the paper I mentioned. And so if we could just leave the Zoom open, and I'll try to find that link really quick.
Okay, no problem.
I know it's in my email box, so I've just got to open it up. But thanks everyone for coming. I appreciate everyone taking their time. I'm glad 300 people did not show up.
Yeah, we have more than 300 people today.